Okay, hey everyone. In this video we are going to quickly go over a Norton equivalency problem. So we have a circuit here and we want to find the Norton equivalent circuit at terminals A and B. So for us, we know what the final thing should already look like, given that they said it should be in a Norton equivalent. So we should have a current source, call it I sub n for Norton current, in parallel with some resistance, not RTH but RN, which ultimately are the same thing, but you have a current source in parallel of a resistance. And now you draw back in your A and B, and then you can say you're done, but of course you'll have to figure out what IN is and what RN is. So to get IN, what you have to do is you have to short your output terminal. So you short A and B. So in this case, that's already been done for you, because you have this pink wire right here, so I don't actually need to draw this in. So ultimately what you really want to do is you find out what current this is traveling on that wire, and that's your Norton equivalent current, or your short circuit current rather. And then later, when you want to find what R sub n is, what you'll do, let me move this out of there. Actually, let me make a copy of this. Okay. Copy, paste. That's not what I want. Okay. Try one more time. Yeah, that's a little better. Okay. Copy, paste. Okay, so that's the original picture on the left. On the picture on the right, we're going to show how we have to set up this circuit in order to get R sub n. So let's get rid of the I sub n for now. So we know when we want to find the equivalent resistance of a circuit, we'll have to turn off any independent sources. In this circuit here, there is only one independent source, and it's this voltage source here. So you're going to switch this from 10 volts to 0 volts, because that's what turning it off means. And so if this is a 0 volt source, that's the same thing as just a straight wire shorting where that voltage source used to be. And that's correct from a circuitry level, because a wire means that there's no voltage drop across it. So now the last thing you have to do is, or what you would normally do is you would look in from A and tally up all the resistances you see as you work your way toward B. But in this case, you can't do that because there's a dependent source. So what we do instead is we hook up a little test voltage or a test current. It's up to you, whichever one you like. But you hook this up here. In this case, I'm going to choose a test voltage. I'll call it VT. And we're going to solve to get what the current is, I sub t, coming out of it. We're going to figure out what that is. And you might be able to do that, of course, using mesh analysis or nodal analysis. In this case, it would be smarter to use nodal analysis because there are only two independent nodes. So that would be the wise choice here, versus 4 equations if you were to do mesh analysis. So you do nodal analysis here at these two nodes, 1 and 2. You'll solve for IT, and you know what VT is because you're the one supplying VT, so you can make this an arbitrary voltage if you want, make it 1 volt. And then ultimately, to get R sub n, all you need to do is use Ohm's law. So you divide VT divided by IT. The idea is, this is your test voltage. You're figuring out how much current's being pulled out of it. You find the ratio, and that's your equivalent resistance of the circuit, seen from terminals A, B. And then once you get that value, you fill it in here with the existing circuit that we have, and there you have your Norton equivalent circuit. Thanks.